should lie in homotopy classes of maps from this to BGO, because this is a fibration sequence, so it passes to an exact sequence of I guess sets. So a class here, i.e. mu, will come from a class here if and only if it vanishes over here. So I want the inclusion. So this is nu, this is bg, this is bg over O. I want this thing to be null homotopic. So that's the first thing to consider, and there'll be much more about that later. This is the normal invariance of, well, there'll be more about that later. So the second thing to talk about is now we can make more examples of p-spaces that aren't manifolds. So I guess we have to find a Spivak normal fibration that doesn't reduce to a vector bundle, and then we know that the underlying CW complex can't be homotopy to a manifold. So the example that I've read is from Gitler Stashev. This is 65. So it's called the paper as the first exotic class of BF. So I haven't actually talked about F, and F is quite a big part of what's going on here as well. So F is the, so recall G was the monoid of homotopy equivalences between S to the k-1. So F is the monoid of pointed homotopy equivalences. And there is a fibration, F to G to S to, I guess, this should be a K maybe. It's a fibration to like this. And then in the limit, as you take these fiber-wise joins, it turns out that BG is BF. So, I mean, this is an important part of it, but I cut it out for brevity. So, in fact, when it says an exotic class of BF, it means equivalently exotic class of BG, so a class of BG that doesn't lift to BO. So they produce a fibration. So spherical fibration, and in fact, E is the p-space that we're interested in. So E is a p-space. Not homotopic to PL manifold. Okay, so they use this obstruction is how it's done. They show that it has non-vanishing classes that characterize this obstruction. So how am I doing for time? Okay, I'll just say this last thing because I thought it was really interesting. Is how Stiefel-Whitney classes come into this whole thing. So I mentioned it before in that sort of table I drew. So I've always known this fact that Stiefel-Whitney classes are invariants of the homotopy type, as opposed to Pontryagin classes or Chern classes, which aren't. But the reason for this is that they're actually invariants of the underlying spherical fibration, which is a homotopy invariant, whereas a vector bundle isn't. Yeah, homotopy invariant of the base manifold, I guess. Okay, so the definition. So this is from Adams, infinite loop spaces. So the ith Stiefel-Whitney class of a spherical fibration is, so let's say phi is whatever Thom isomorphism we want to use. Phi is a Thom isomorphism. SQI is the ith steamroll square. So we define it like this. So we take, so again, the reduced cohomology of the Thom space of P. So we take the steamroll square, so that should shift us up by I to, again, the reduced cohomology of the Thom space. So we're going to get Thom isomorphisms here. So that should be 2m. So it should be m of the base space. And again, but now shifted up by I. M of plus I of the base space. So we're going to have an element 1 here. So it passes around here. And this is going to be, yeah, this is pretty important, otherwise it's a Wu class. Everything with Z2 coefficients. So then the ith Stiefel-Whitney class is defined to be the composite of these maps. So I guess that's Wi of the sphere bundle is defined to be so and you can show that these Stiefel-Whitney classes coincide with the Stiefel-Whitney classes of a vector bundle if the sphere bundle comes from that vector bundle, which is, I think, saying something quite deep about what they really are. So I think that's all I had to say.